So in this discussion, I want to talk about what is the unit step function and its related function, which is effectively its derivative, which is the impulse function. And these functions turn out to be really, really important for all sort of handling of linear systems. The very first thing is that the unit step function is just very important because it allows you to sort of have a mathematical framework to talk about effectively flipping a switch. So if you're someone who likes to look at circuits or physical things or other mechanical things, the whole ability that I had something work and then I flipped a switch and something else is often mathematically represented by this sort of u of t function. And so this becomes really important to start with, but it also becomes important mathematically with what might be important here as well. So let me define what this is. In the u of t in the continuous case, it's a function that's 0 and then becomes 1 after time equals 0. And so that's sort of the mathematical definition. Its discrete time form is very similar. It's effectively, imagine the sampled version of this, where it's pretty much 0 all the way through until n equals 0, and then it becomes 1 all the way through. And you think, okay, that's a very interesting function. It's a sort of clearly a step. It's pretty straightforward why you think of it as a step. And again, it's the classic thing of, oh, I have some function, I have the sum system, and physically I can put in a step function. I just change a value and I want to see what it now does. I change a value and I want to see its response. This makes a lot of sense. Now, what happens, of course, though, is that much of linear system theory is based on what are impulse responses, which is a lot harder in sort of continuous space to physically build. Discrete space a little bit easier to actually put into a system, but it's not necessarily the first thing you would think about. But it's basically the derivative of this function, and it just turns out a lot of the mathematical theory formulates very nicely in this approach. We probably could have formulated everything with unit step functions, but in the end, it was a bit easier to think about this in impulse functions, and this is how the theory and the way it's typically looked at. The impulse response functions, if I look in discrete, is basically just the derivative of either of these cases. Now, the derivative in discrete time just means that this step gives me a 1, and everywhere else it's constant, so it's just going to be 0. In the continuous time case, it's pretty much 0 everywhere, or pretty much constant everywhere, so I get 0. Again, very reasonable. Except at the step, I get this jump. And not only is it sort of a jump, but it's like infinitely big. And so mathematically, this makes you work a bit harder to really make sense of this, because it's like 0, 0, and it's infinite. And you know that the integral of this function has to be 1, because this is, in fact, the integral of the original function. So it's a very interesting structure, and it requires a lot of discussion in and of itself, just mathematically how to represent it. But assuming that this is basically something that happens only at 0, basically, and effectively has infinite size such that when I integrate it, the total area under that curve is 1, is what I'm looking at for my function. This is often called an impulse, particularly because the continuous time case, it looks like it is this incredibly steep thing that creates a jump. What it actually does practically in a typical differential equation is it basically looks like I simply just kept everything the same and just moved the initial condition typically. Now, there's always exceptions to this. Whereas the step response basically looks like I've actually changed a parameter, and I may have moved an initial condition as well, depending on what I'm doing. This is useful because it basically means that if I'm working with autonomous differential equations, I stay there. And I stay in that space, and often those are easier systems to solve, which is why a lot of people like to look at it. A lot of this theory came about of saying, how do I solve arbitrary differential equations? And what it turned out is that you could say, let me take an impulse, and it became the way to break up any signal into groups of impulses. Now, maybe infinitely thin numbers of impulses in the continuous time form, discrete time form, maybe it's more obvious, there's bunches of pieces there, But either way, it's the same sort of basic conversation here, where I might take a discrete impulse, it's delta of n, which is 1 or 0, and then if I delay it, I just simply have a shift in the argument. Okay, this turns out to be extremely valuable because what it allows me then to do is then to say, imagine I have an impulse response, and I have an x of t, or a delta of t, or a delta of n. And I say, all right, what would I get for that response out of the h of t or h of n? And that sort of dynamics immediately will tell me things of whether this is stable, whether this is unstable, whether I'm getting an oscillatory, whether it's a finite impulse response. FIR means impulse. What is the impulse response? And is it finite? Is it infinite? And if I have that response, I can use that, and by basically breaking up the other input into a whole bunch of these delta functions, I can then solve it, which is typically known as a process as convolution, which is exactly what you're looking for there. So this whole approach is a very, very rich concept based on what is two very interesting and a little bit unique functions. And so that's why it's really important to think about these functions, because these are going to get used ubiquitously in almost anything where we look at linear systems and sort of what kind of dynamics do I get in a linear structure.